channel Crisp ML. This is Parijat here. Today we'll be discussing how gradients are calculated and what is the role learning rate plays, and we will see this using some live examples. We will take up some simple examples and we will try to simulate their values both in Excel and in Python editor. How the calculation is actually done, we'll try to understand, and how we can develop the intuition about that. So all of us would have used or worked with gradients, or at least would have heard about it when we are applying many ML techniques, especially the gradient descent technique. But sometimes we don't have an idea of what is actually going on in the background, or we may not be able to fully appreciate what exactly is happening, and not have that clarity of thought. So first we will take up a simple equation. Let's say y is equal to a square plus b square, and we'll take up a fixed value of y and we'll try to estimate a and b, and we will adjust the values of a and b using the gradients. Then what we'll do is we'll take up a single neuron, and what we'll try to do is we'll see how the single neuron functions. So a neuron has, as you would be knowing, a weight and a bias parameter. So how weight and bias parameters gets updated, and we will use a log function as a data set. Okay? And of course we'll show this simulation live to you, how the weights and biases are updated in this case. Required for understanding is the knowledge of partial derivatives. So this should not be very difficult. It is high school math. I will be explaining this clearly, so even if you have some idea about differentiation or integral calculus, this should be easy to pick up. Of course, the basics of neural networks, because this is where the concepts are heavily used, and this is what we are taking here as an example as well. And some idea about PyTorch. This video itself, the code that I'm going to show you is very, very intuitive. If you know some basic Python programming, you should be able to pick it up. So as we discussed, we will first take this equation, y is equal to a square plus b square. We will take a and b as two tensors which have gradients attached when we are computing the values for a, and so we will just take a fixed value of y as, let's say, y actually equal to 200, and then we will try to estimate which values of a and b come closest to satisfying this equation for y equal to 200. So our y actual here will be 200, and this is the target we are planning to reach. As you know, we will need a loss function. So loss function is something which tells us how far we are from our desired target or destination. So here we will use mean absolute error, and that is the absolute value of y actual minus y. We've kept this. So of course there's no mean here because we have only one data point, as we saw, y actual equal to 200, and we will have multiple epochs but no mean here. Okay, so it's just absolute error. Now how will we update the weights of a and b? As we said earlier, we will initialize the weights at a certain value, and then based on the loss function we will compute the gradients. Now the gradient here is nothing but the partial derivative of the loss function with respect to a, so that is the gradient for a, and the partial derivative of b with respect of the loss function with respect to b, that will be the gradient for b. So to develop the intuition about this is, when you have the loss function, which is actually your distance from your actual target. So how does it behave when you change the values of a? So that is conveyed by this partial derivative. Why partial derivative? Because at that moment, since there are multiple parameters, so we will usually take a partial derivative to see the impact of the individual parameters. So for example, here, what impact a will have on the loss function can be found out using the partial derivative of the loss function with respect to a, and similarly for b. Okay, so in partial derivative, all other parameters are assumed to be constant. Okay, and then it is just the derivative of that function with respect to a, assuming all other parameters. Let's say here it will be just b as constant. Once we introduce the learning rate, we will tweak this calculation a little, and we will see the gradient computed as partial derivative multiplied by the learning rate and see what kind of value add or advantage the learning rate brings, and how it helps us converge to a solution. We know y is equal to a square plus b square. Our goal is to calculate the partial derivative of the loss function with respect to a. So we know our partial derivative is this, and so we can use the chain rule. Now what does chain rule say is that partial derivative of the loss function with respect to a can be computed by computing the partial derivative of the loss function with respect to y and the partial derivative multiplied by the partial derivative of y with respect to a. So we know the loss function, we can compute the partial derivative with respect to y here, and we know y's value that is equal to a square plus b square, so we can compute the partial derivative of y with respect to a using this equation. And similarly for the b. So our loss function is this: when y is greater than y actual, we will have a different value. We will not have -1, we will have +1. So let's see how. So imagine this is your y actual. Say y is here. Okay. Now as you can see, y is greater than y actual here. Okay. So you have a certain distance here. Now here, if you change y by a certain distance, see the absolute distance increasing here with y actual, right? So this is the absolute distance. It does not matter what sign it is, what it is, it does not matter that way. So you can see it increasing here. So as you can see, since this is an absolute value, the distance is increasing, so the derivative is +1. Similarly, if y is less than y actual, okay, so if you see here, y is less than y actual, okay. Now here, if you increase y by 1 unit, okay, as you can see, the distance is this much. Now the distance is lesser. You have increased y, which is moving towards the right. Of course, always y is moving towards the right. So when it comes closer to y actual. So we are not considering the sign here. It's the absolute value of the distance. So of course the distance is decreasing. So similarly, the derivative here is -1. Okay, when you increase y, your loss function is decreasing. So when y is less than y actual, it is -1. We have y is equal to a square plus b square. Now if you just take the derivative of this equation with respect to a, you will treat b as constant, and the derivative of a square with respect to a will nothing be but 2a. Similarly, partial derivative of y with respect to b will be 2b. Okay. Now we have both the pieces of puzzle in place. We know the partial derivative of the loss function with respect to y. It is +1 when y is greater than y actual, -1 when y is less than y actual. And the partial derivative of y with respect to a is nothing but 2a. And similarly for b, it is similar. The first part is similar, and partial derivative of y with respect to b will also be similar. It will just be 2b. Let's see how this works out in a spreadsheet. So what we will do is, so we will have this epoch, we will have A, we will have B, we'll have A, we'll have B, we will have Y, okay, we will have Y actual, and we will have the gradient for A. I'm using the $sign. You can use any sign. I'm just using it out of just it's a random choice. Okay, let's make it proper. So let's make it partial derivative of the loss function with respect to B. Alright, now in our first epoch, we will keep a particular value. So I have also put this simulation on PyTorch here. I will be discussing this code shortly with you. So I've initialized this to tensors 5 and 6. So let's take the same values here, 5 and 6. This is just a random starting choice, and maybe you could take up a better choice here and tell me in the comment section below whether how it impacted your results, whether the results were better, whether it converged faster, whether it was more accurate. So forgot one thing. This will be your loss function E, which is nothing but absolute value of y actual minus y. Okay, so y is nothing but p square of this plus this. Okay, y actual being is 200 loss function. So here we have seen, so the error is nothing but the absolute value of y actual minus y. So here the gradient will be composed of two parts. The first part will be the so let me make a column for this. Let's take the gradient of E with respect to y to make it clearer. So if y is less than y actual, it is -1, otherwise it is 1. Okay, and finally this is nothing but this piece multiplied by 2 times a. Similarly for b, it is nothing but this multiplied by 2 times b. Okay, so in the next epoch, how will we update this? So let's see. So now as per our formula, it will be the previous value minus the gradient for a. Similarly for b, it will be the previous value of b minus the gradient for b. Okay, formula will remain same, y actual will remain same. All these values will also remain, formulas will also remain same, so we'll just drag it, and now from here onwards you can just we will, let's say, do it for 10 epochs. Okay, and we can just drag this here. Okay, so what do we see? We see that running in 10 epochs, our value is, first we started at 5 and 6, but after that the value is just bouncing between 15 and -15, 18 and minus, for value of A is 15 to -15, 15 to B is just between 18 to -18, and so on. Y is fixed at 549, of course, because it's the square of both the values, square addition of both the values. Y actual is 200, error is constant at 349, so it is not changing at all. Okay, so there is no learning, no improvement at all. Even if you extend this to multiple epochs, there will simply be no learning here. So, but this is the way it is calculated. So how do we check this? Let's go to the Python code. We have kept torch, we have kept y actual equal to 200, number of epochs is 10, and the value for tensors A and B is 5 and 6. Okay, we have used the learning rate, we'll use it later, but I just kept it for calculation. So now it's not used anywhere here. What we'll do is, for number of epochs, that is 10, we will first print the epoch number, and since in Python it will start from 0 to 9, so we'll just print it i+1 so that we can match it to our Excel sheet here. And then we will first print the value of A and B for whatever it is. Then we will compute the y and we'll print the value of y. We will calculate the loss, which is y absolute value of y actual minus y, and we'll print that loss value. Then we will do a backward propagation here, okay, and after that we will print the gradients for A and B, okay. And after that we will detach for some time from the torch, so that this updating the gradients does not come in the computation graph of PyTorch. So PyTorch makes a graph of all the calculations. So while doing loss.backward, it will consider whichever variables have gradients attached. It will see all the calculations associated with that variable and then do a gradient calculation. So we don't want this updating thing to be there in that graph. So we will just simply detach it. Okay. So after that we will enable the gradients. So let's run this code and see whether we can match the same values which we are getting with the spreadsheet that we just saw. Okay. So I'm running this code. We'll first import torch and initialize the value, will print, and just run it till here. Okay, our tensors are initialized to 5 and 6. Alright, now for number of epochs, we will just run it and see whether the gradient calculation matches. Alright, so let's check. On the first epoch, the loss is 139, the value of A and B are 5 and 6, Y is 61, the gradient is -10 and -12. I think this matches. 5 and 6, Y is 61, the loss is 139, and of course the gradient values are -10 and -12. For the second epoch, the value of A and B are 15 and 18 respectively, which is also matching here, and the Y value is 549 and the loss is 349, and the gradient values are 30 and 36. So which is matching here. So similarly, if we go on, okay, we go on. So we will see it's fluctuating. So let's say in the 8th epoch, it is 15, 18, 549, 349, 30 and 36. So 15, so this is the 5th epoch, 15, 18, 549, 349, 30 and 36. And similarly in the 10th epoch, we have this value. So it is matching with the calculation, and this is so our calculation in the spreadsheet is correct. We see that this is not learning. So let's see if we can. Now let's introduce the learning rate. We call it LR, okay, and we will put it on an initial value of 0.01, okay, and we will keep this value constant throughout all the epochs. Okay, and now where do we need to change? So if you remember the value while we are updating, we need to multiply the gradient with the learning rate. So that's what we will do. We will multiply it with the learning rate before subtracting it from the earlier value. We will do the same thing for B, multiply the learning rate with the learning rate, gradient value. So this is what we've changed, and we will drag this computation down till here. Okay. Now if you can see, the loss is decreasing. Okay. So we are actually learning something here. Okay. So let's see. If you insert a chart now, so if you see this here, we are learning. As the loss is decreasing, we are learning something, right? All right, let's go back to the Python editor. So here learning rate is 0.01. Now let's implement that change here as well. So our learning rate. Okay, then let's run this whole thing again. So great. Let's also add one more parameter here, the total loss across epochs. Actually, that's not the right thing, but yes. So let's see. The loss in the last epoch is 112.8769. So I have rounded it to 112.877, which is almost exactly matching here. tensor value for A is 5.9755, 97546, which is, of course, it is rounded to 4 decimals here. So, which is matching 7.1706, again 055. This is also, if you round it, will become 1706. It is matching. The Y value 87.1230, 0.211. That's also matching. Similarly, and the gradients. So the gradient here, if you calculate, will be minus 11.9509 and minus 14.3411, which is exactly matching. So our calculation is correct. So this is a simple thing, but just for fun, I mean, let's extend this and see if we are able to converge, and which value of A and B comes closest to 200. Okay, let's see. Let's take these 2 rows. Why taking 2 rows to drag? So that 200, 200, this row will be dragged as 200 only, and the learning rate also will be dragged as. So let's extend it till 25 epochs. We have come to 42. So we are coming closer. Let's extend further. Okay. So what do we see here? We have come to 0.1017 as well. That's pretty close. After that, it's slightly increased. Then again, jumped to 7.8. Then again went down. Jumped to 7.7. Again went down. Then went back to 0.656, and so this is now bouncing off in a certain area at the bottom. Okay, so if you see, it has pretty much reached its absolute minima here at 33rd epoch, and if you plot the graph here, you see how it has reached the bottom and it's almost oscillating there. So that's what we need. So it's almost converged here, and we can safely say that at the 33rd epoch, maybe, here these values come pretty close, 9.05318 and 10.8638. So this is how the learning rate simplifies. Alright, thanks for watching. That was it for this video. In the next video, we will take the case of a single neuron, and we will try to learn the log function, and we will also try to match it with the result of PyTorch implementation and see how the results match, and develop an intuition about the gradients and the learning rate.